What if I told you that the answers to one of humanity's oldest questions, are we alone in the universe, might be hiding in the light of distant stars? For centuries, we've looked up at the night sky, wondering if other worlds like ours exist. But today, we're not just wondering, we're decoding the very atmospheres of planets light years away, searching for the fingerprints of life. This isn't science fiction anymore. It's real, it's happening right now, and the discoveries we're making are rewriting our understanding of the cosmos. Think about it. Every exoplanet's atmosphere is like a cosmic message in a bottle, drifting through space. The way light filters through those alien skies carries secrets, traces of water vapor, oxygen, methane, even potential signs of biological activity. Scientists are like interstellar detectives, piecing together these clues with tools like the James Webb Space Telescope, which acts as a universal translator for these distant whispers. And what they've found so far is astonishing. Planets with skies of molten metal, worlds where it rains glass, and just maybe places where conditions could be just right for life as we know it. But here's what's truly mind-blowing. This isn't just about finding another Earth. It's about redefining what life could look like beyond our solar system. Could there be organisms thriving under alien suns, breathing atmospheres we've never imagined? The hunt for habitable exoplanets is more than a scientific quest. It's a journey into the unknown, one that challenges everything we think we know about our place in the universe. So buckle up, because we're about to dive deep into the art and science of deciphering exoplanet atmospheres, where every molecule tells a story, and every discovery brings us one step closer to answering the ultimate question: is there life out there? Finding planets beyond our solar system is like trying to spot a firefly hovering near a lighthouse from thousands of miles away. The sheer brightness of a star makes its tiny orbiting worlds nearly invisible to our telescopes. So how do astronomers pull off this cosmic magic trick? They've perfected ingenious methods to detect the subtle clues these distant worlds leave behind. One of the most successful techniques is called the transit method. Picture this: when an exoplanet passes in front of its host star from our perspective, it blocks a minuscule fraction of the star's light, like a gnat flying across a car headlight. Space telescopes like Kepler and TESS monitor thousands of stars simultaneously, watching for these telltale dips in brightness. A single transit might not reveal much, but when it happens repeatedly at regular intervals, voila, you've found a planet. Then there's the radial velocity method, which detects the gentle wobble of a star caused by the gravitational tug of an orbiting planet. Imagine a spinning figure skater holding hands with a partner. The skater's motion shifts slightly as the partner moves around them. In space, these subtle stellar wobbles reveal not just a planet's presence, but also clues about its mass. These two techniques have turned exoplanet hunting into a thriving scientific field, with over 5,000 confirmed worlds in our galactic neighborhood. But here's where things get even more fascinating. Once we spot an exoplanet, the real detective work begins. Not all planets are created equal. Some are gas giants, others are rocky, and a precious few sit in the so-called Goldilocks Zone, where temperatures could allow liquid water. The next challenge, peering into their atmospheres. That's where advanced tools like spectroscopy come into play. When starlight filters through an exoplanet's atmosphere during a transit, certain molecules absorb specific wavelengths of light, leaving behind a chemical fingerprint. By decoding these patterns, scientists can identify water vapor, carbon dioxide, methane, and even potential biosignatures, gases that might hint at life. Every discovery adds a new piece to the puzzle. Take the TRAPPIST-1 system, for example, 7 Earth-sized worlds orbiting a cool dwarf star, 3 of which might have the right conditions for liquid water. Or the mysterious super-Earth K2-18b, where recent observations suggest water vapor in its atmosphere. These aren't just data points, they're windows into the incredible diversity of planets that fill our galaxy. And with next-generation telescopes pushing the boundaries of what we can observe, we're standing on the brink of discoveries that could forever change how we see ourselves in the universe. An atmosphere isn't just a blanket of gas, it's a planet's autobiography written in chemistry. The air surrounding a distant world holds answers to questions we're only beginning to ask. What is this planet made of? How scalding or frigid are its surface conditions? Most tantalizing of all, could invisible biological processes be altering that alien sky? When starlight pierces through an exoplanet's atmospheric layers, it doesn't just dim, it transforms. Molecules within that alien air act like microscopic barcodes, selectively absorbing very specific wavelengths of light. Scientists read these absorption patterns like cosmic grocery lists, identifying ingredients from carbon dioxide to methane with astonishing precision. Take water vapor, for instance. Its telltale signature in an exoplanet's atmosphere suggests more than just moisture. Liquid water requires just the right temperatures and atmospheric pressures, meaning that detection could point to habitable conditions. Oxygen presents an even more intriguing puzzle. On Earth, our abundant oxygen exists almost entirely because of photosynthesis. Could the same be true on another world? Then there's methane, which on our planet mostly comes from biological sources like bacteria and livestock. When these gases appear together in an exoplanet's atmosphere, especially in proportions that can't easily be explained by geology alone, it sets off scientific alarm bells for potential life. But the universe loves throwing curveballs. Consider Venus, a planet with an atmosphere so thick with carbon dioxide that its surface could melt lead, demonstrating how atmospheric composition dictates extreme climates. Or Jupiter's moon Titan, where nitrogen and methane form an atmosphere denser than Earth's, complete with hydrocarbon lakes and rain. These examples in our own solar system prove that habitable atmospheres might look nothing like ours. Some exoplanets could harbor life breathing hydrogen instead of oxygen, or thriving under skies filled with exotic compounds we've barely studied. That's why modern telescopes don't just hunt for Earth clones. They are searching for atmospheric anomalies that rewrite the rules. When the James Webb Space Telescope detected sulfur dioxide in an exoplanet's air for the first time, it revealed active chemistry we'd never predicted. Other worlds show traces of titanium oxide or silicate clouds, materials that could create permanent twilight zones where temperatures stay stable for billions of years. Each discovery stretches our imagination further, proving that the recipe for life might be far more flexible than we ever dreamed. The real magic happens when multiple lines of evidence converge. A planet in the habitable zone with water vapor, intriguing. Add methane and an ozone layer, now we're seeing something that demands deeper study. Future telescopes will analyze how these atmospheric ingredients change with seasons or rotate across a planet's dayside, dynamic clues that could reveal oceans, continents, or even industrial pollutants from advanced civilizations. Every atmospheric fingerprint we decode brings us closer to answering whether life is a cosmic fluke or an inevitable spark waiting to ignite across the galaxy. Imagine a planet where the temperature is just right, not so hot that oceans boil away into space, not so cold that everything freezes solid, but perfectly balanced for liquid water to pool on its surface. This cosmic sweet spot is what astronomers call the habitable zone, or more poetically, the Goldilocks zone. It's the orbital real estate where a planet receives just enough starlight to keep water in its liquid form, a key ingredient for life as we know it. But here's the catch: being in the right neighborhood doesn't guarantee a welcoming environment. A planet could be perched perfectly in this zone and still be as barren as a desert or as hostile as a pressure cooker. Take our own solar system as an example. Venus and Mars both technically sit within the Sun's habitable zone, yet neither could support life today. Venus suffers from a runaway greenhouse effect, with surface temperatures hot enough to melt lead, while Mars's thin atmosphere can't trap enough heat to maintain liquid water long-term. This tells us something crucial: distance from a star is just the starting point. A planet's atmosphere acts like a thermostat, regulating temperatures and creating the conditions for habitability. A thick blanket of greenhouse gases can turn a Goldilocks planet into a hellscape, while too thin an atmosphere might leave it frozen and lifeless. That's why astronomers get so excited when they find worlds like Kepler 186f, an Earth-sized planet orbiting comfortably within its star's habitable zone. But the real intrigue begins when we study its atmosphere. Does it have the right mix of gases to stabilize temperatures? Could clouds reflect just enough starlight to prevent overheating? Even more fascinating are the outliers, planets that defy expectations. Consider tidally locked worlds, where one side permanently faces their star while the other languishes in eternal night. Their atmospheres might redistribute heat in unexpected ways, creating narrow bands of temperate conditions along the twilight border between scorching day and frigid night. The search for habitable exoplanets isn't just about finding Earth twins. It's about uncovering the full spectrum of possibilities. Some stars, like red dwarfs, have habitable zones so close that planets within them experience extreme tidal forces and intense stellar flares. Others, like larger, hotter stars, might host Goldilocks planets with years shorter than an Earth week. Each scenario challenges our assumptions about what makes a world truly livable. With every new discovery, we're not just mapping planets, we're rewriting the very definition of home. Breaking down starlight into its chemical secrets is like teaching sunlight to talk. When an exoplanet glides across the face of its star, it doesn't just block the light, it transforms it. The planet's atmosphere acts like a cosmic filter, imprinting its unique signature onto the starlight that manages to pass through. This is where spectroscopy becomes our universal translator. By splitting that filtered light into a rainbow-like spectrum, scientists uncover dark absorption lines, tiny gaps where specific gases have stolen away certain wavelengths. Each missing piece of light tells a story. A dip at 630 nanometers, that's the calling card of oxygen. A cluster of lines near 3.4 microns. Hello, methane. The precision of this technique borders on miraculous. Consider that we're detecting molecules billions of miles away by studying shadows within starlight. The James Webb Space Telescope spectrographs can distinguish between carbon monoxide and carbon dioxide in an exoplanet's atmosphere as easily as a sommelier identifies notes in a fine wine. But the real magic happens when these spectral fingerprints start forming patterns. On Earth, oxygen and methane coexist in our atmosphere because life constantly replenishes them. They're like two ends of a seesaw that biology keeps in motion. Finding that same unstable balance on another world would be a game changer. Yet spectroscopy doesn't just reveal ingredients, it exposes atmospheric drama. Take the case of WASP-76b, a planet so hot it vaporizes metals. Its spectrum showed iron absorption on the day side but none on the night side, suggesting molten iron rain. Then there's HD 189733b, where silicate particles in the upper atmosphere scatter blue light, giving the planet a perpetual azure haze. These aren't just data points, they're weather reports from alien worlds. The challenges are as revealing as the discoveries. Some exoplanet atmospheres appear cloudy, not with water vapor, but with exotic condensates like sodium sulfide or zinc chloride. Others show inverted temperature profiles, hotter in the upper layers than near the surface. Each anomaly forces us to rethink planetary science. Spectroscopy isn't just answering questions, it's showing us how much we didn't even think to ask. As we refine these techniques, we're not just decoding light, we're reading the diaries of distant worlds, one spectral line at a time. The James Webb Space Telescope isn't just another instrument, it's our generation's time machine, peeling back the layers of exoplanet atmospheres with capabilities that would have seemed like pure fantasy just decades ago. Unlike Hubble's visible light focus, Webb's infrared eyes detect the heat signatures of distant worlds, revealing atmospheric chemicals invisible to other telescopes. Imagine trying to study a candle's flame from 1,000 miles away, then suddenly being handed thermal goggles. That's the leap Webb represents. Its very first deep look at exoplanet WSP-39b demonstrated this power spectacularly. In a single observation, Webb spotted water vapor, sodium, potassium, and most remarkably carbon dioxide. Detecting CO2 on a planet 700 light-years away isn't just a technical achievement, it's a paradigm shift. Carbon dioxide is a key atmospheric regulator, influencing climate and potentially even hinting at geological or biological activity. But Webb didn't stop there. The telescope's sensors revealed sulfur dioxide in WSP-39b's skies, evidence of active photochemistry, where starlight triggers complex chemical reactions. This was the first time such processes had been detected outside our solar system, proving that exoplanet atmospheres aren't static blankets but dynamic, evolving systems. What makes Webb truly revolutionary is its precision. Earlier telescopes might confirm the presence of water on a distant world, but Webb can tell us whether that water is concentrated in clouds or distributed evenly through the atmosphere. It can distinguish between methane produced by geological vents versus potential biological sources based on isotopic signatures. The telescope's recent study of K2-18b, a Haitian world with a hydrogen-rich atmosphere and possible water oceans, detected dimethyl sulfide, a molecule on Earth produced exclusively by living organisms. While the finding requires confirmation, it showcases Webb's ability to hunt for life's molecular whispers. Yet perhaps Webb's greatest gift is its capacity for surprise. The telescope has already upended expectations by finding planets with clear skies where models predicted thick clouds, and others with bizarre atmospheric compositions defying all classification. Each discovery forces us to rewrite planetary formation theories. As Webb turns its golden mirror toward more exoplanets in the coming years, we're not just collecting data, we're learning an entirely new language of planetary diversity, one that may ultimately contain the vocabulary of alien life. Detecting life on another world isn't about spotting little green men, it's about reading the chemical fine print in an exoplanet's atmosphere. Certain molecules act like cosmic neon signs, hinting at biological activity. Take oxygen, for example. On Earth, our oxygen-rich atmosphere exists in constant partnership with life. Plants and algae pump it out, while animals breathe it in. Without this biological cycle, oxygen would quickly vanish, reacting with rocks and oceans. So when we detect substantial oxygen in an exoplanet's air, especially alongside methane, a gas that oxygen normally destroys, it sets off scientific fireworks. These two gases coexisting is like finding smoke and fire together, but the universe loves playing tricks on us. volcanic activity can produce oxygen without any life involved, as can the breakdown of water molecules by intense starlight. Methane, too, has its imposters. Geothermal vents and comet impacts can release it in abundance. That's why scientists look for more than just individual ingredients. They search for the entire recipe. A planet with oxygen, methane, water vapor, and nitrous oxide in specific ratios starts to look suspiciously like a world where something is breathing, growing, or metabolizing. The real challenge comes when we encounter atmospheric cocktails we've never seen before. Imagine an exoplanet where dimethyl sulfide fills the air on Earth. This pungent gas comes exclusively from marine algae. Or phosphine, which in our experience only appears where life exists or in the extreme pressures of gas giants. Finding these molecules on a rocky world would be staggering, but we'd still need to rule out every possible non-biological explanation. That's why researchers are building libraries of atmospheric models, simulating how volcanic planets, water worlds, and hydrogen-rich environments could mimic life's signatures. Future telescopes won't just sniff out chemicals, they'll track how atmospheres change over seasons. A sudden bloom of oxygen in an exoplanet's springtime, followed by a summer dip, could mirror Earth's annual plant growth cycle. Or imagine detecting chlorofluorocarbons, gases with no natural source that might indicate industrial activity. The hunt for biosignatures is evolving from a chemical snapshot to a dynamic search for patterns that whisper, shout, or even dance the story of alien life. Every atmospheric puzzle piece brings us closer to the ultimate discovery, not just that life exists elsewhere, but that the universe might be teeming with it. While biosignatures might reveal microbial life or oxygen-producing algae, technosignatures could be the universe's way of shouting, "Someone built something here." These aren't just chemical traces, they're potential evidence of civilizations advanced enough to alter their planet's atmosphere or harness energy on a cosmic scale. Imagine detecting chlorofluorocarbons in an exoplanet's air. On Earth, these ozone-depleting compounds only exist because of human industry. Or spotting the glow of city lights on a planet's night side, a telltale spark against the darkness. Even more exotic possibilities exist, like Dyson spheres, hypothetical megastructures built around stars to capture their energy-leaking infrared radiation that our telescopes could pick up. The search for technosignatures forces us to rethink what intelligence looks like across the cosmos. Our own technological footprint has changed dramatically in just a century, from radio waves to space debris. An alien civilization millions of years older than ours might manipulate matter and energy in ways we can't yet fathom. Some researchers scan for narrowband radio signals, the cosmic equivalent of a deliberate hello. Others look for unnatural atmospheric compositions, like industrial nitrogen dioxide or synthetic greenhouse gases stabilizing a planet's climate. Even the sudden disappearance of a star's light could suggest massive construction projects orbiting it. Yet the hunt comes with fascinating paradoxes. A civilization advanced enough to build planet-scale technology might also be smart enough to hide its presence. They could transition to clean energy, leaving no atmospheric pollution, or communicate via methods we haven't discovered yet. That's why scientists cast such a wide net, studying everything from laser pulses to unusual heat distributions on exoplanets. The Breakthrough Listen project analyzes petabytes of radio data, while telescopes like Vera Rubin will monitor millions of stars for fleeting anomalies. What makes technosignatures uniquely thrilling is their potential to answer not just whether life exists out there, but whether thinking, building, dreaming beings like us exist. A single detection could reveal that intelligence isn't a fluke. It's a natural outcome of cosmic evolution. Until then, every atmospheric anomaly, every unexplained light pattern invites us to wonder, could that be the first chapter of an interstellar conversation? The search stretches our imagination to its limits, challenging us to consider not just what life is, but what it might become. Some planets don't just push the boundaries of what's possible, they shatter them entirely. Take hot Jupiters, for instance, gas giants so close to their stars that their atmospheres reach temperatures hotter than some furnaces. These cosmic oddballs orbit their suns in mere days, sometimes even hours, with skies broiling at over 2,000 degrees Celsius. At those extremes, metals like iron and titanium don't just melt, they vaporize, creating clouds of molten droplets that reflect light like alien mirrors. Winds whip across these planets at thousands of miles per hour, carrying vaporized rock from scorching daysides to slightly cooler nightsides, where it condenses and rains down as liquid gemstones. Yet these extreme conditions reveal surprising truths. When the Hubble Space Telescope observed hot Jupiter HD 189733b, it detected a stratosphere, a layer of atmosphere where temperature increases with altitude, just like Earth's. But instead of ozone-absorbing ultraviolet light, this exoplanet's upper atmosphere sizzles with titanium oxide, a compound so rare in Earth's skies that finding it here was like stumbling upon a cosmic chemistry experiment gone wild. These discoveries force scientists to rethink how atmospheric layers form under unthinkable heat and pressure. On the opposite end of the spectrum lie super-Earths, rocky worlds up to 10 times more massive than our own. Some might resemble scaled-up versions of Earth, but others wear thick, crushing atmospheres more like Neptune's, or toxic shrouds of carbon dioxide rivaling Venus. The planet Gliese 1214b, for example, orbits so close to its dim red star that its entire atmosphere might consist of superheated steam, trapped under pressures that turn water into an exotic, high-density fluid. Others, like 55 Cancri, could have surfaces blanketed in lava oceans, with atmospheres of vaporized rock that condense into mineral clouds on the night side. What makes these extreme worlds so valuable isn't just their novelty, it's how they stress-test our theories. Hot Jupiters shouldn't exist according to early planetary formation models, yet their prevalence suggests our understanding of gas giant migration is incomplete. Super-Earths, absent from our solar system, show how rocky planets can evolve under different gravitational rules. Each scorching gas giant or molten super-Earth is a natural laboratory, revealing how chemistry, weather, and geology operate under conditions we could never replicate on Earth. The most thrilling part, these aren't just scientific curiosities, they're signposts pointing toward the incredible diversity of planets waiting to be discovered. If the universe can craft worlds where it rains rubies or where skies glow with metallic vapors, what other atmospheric marvels might be out there? Every extreme exoplanet we study stretches the boundaries of what we consider possible, reminding us that the cosmos thrives on variety. Clouds on distant worlds aren't just fluffy decorations, they're wild cards that can completely reshape how we read an exoplanet's atmospheric secrets. Imagine trying to study Earth's chemistry through a thick blanket of fog. That's the challenge astronomers face when silicate particles or metallic vapors shroud an alien world. These aren't water droplets like our familiar clouds. Some exoplanets boast skies filled with molten sand, where temperatures are so high that minerals vaporize and condense into glittering, opaque veils. Planet Kelt 20b takes this to extremes, with an upper atmosphere so hot it contains gaseous iron and titanium, creating shimmering layers that scatter light in unpredictable ways. What makes these alien clouds so fascinating is their double-edged nature. On one hand, they obscure the very molecular fingerprints scientists desperately want to analyze, masking the absorption lines that reveal atmospheric composition. It's like trying to identify a song while someone drums loudly over the melody. But on the other hand, the clouds themselves tell a story about the planet's climate and weather systems. Take JJ1221b, a super-Earth where thick hazes might be composed of zinc sulfide or potassium chloride, compounds that would form bizarre, reflective blankets high in the atmosphere, potentially cooling the planet below in unexpected ways. The diversity is staggering. Some hot Jupiters exhibit patchy, uneven cloud coverage that changes as they orbit, creating dynamic patterns akin to Jupiter's swirling storms, but with materials we'd consider exotic. Others, like the ultra-hot WASP 76b, may have permanent day-side clouds of vaporized iron that dissipate as metallic rain on the cooler night side. Even warm Neptunes, mid-sized planets with thick atmospheres, show evidence of methane clouds condensing at different altitudes, forming layered weather systems completely unlike anything in our solar system. Decoding these atmospheric curtains requires clever workarounds. Scientists now analyze how cloud properties change across different wavelengths of light, since certain infrared frequencies can pierce through hazes that block visible light. Others study the polarization of starlight filtered through exoplanet atmospheres, which reveals how particles are shaped and distributed. These techniques recently uncovered something astonishing about the super-Earth JJ12124b. Its flat transmission spectrum suggests ultra-high clouds so thick and reflective that they act like a planetary-scale mirror, bouncing starlight away before it can penetrate deeper. Far from being nuisances, these alien weather systems might hold keys to habitability. On tidally locked planets, where one side always faces the star, high-altitude clouds could regulate temperatures by reflecting intense sunlight, potentially creating habitable zones in otherwise scorching environments. Some models even suggest that certain cloud types might protect nascent life from harmful radiation, acting as cosmic sunscreen. Every new discovery about exoplanet clouds forces us to expand our playbook, proving that the universe's weather forecast is infinitely more creative than we ever imagined. Weather doesn't just shape exoplanets, it defines them in ways that make Earth storms look tame by comparison. Picture a world where hurricane-force winds never stop, screaming across the landscape at speeds faster than sound itself. On HD 189733b, a cobalt blue gas giant, winds may reach up to 5,400 miles per hour, so powerful they could shred metal. These aren't temporary tempests but permanent atmospheric rivers, fueled by the extreme temperature differences between a planet's scorching dayside and its frigid night. Tidally locked planets take weather extremes to another level entirely, with one hemisphere perpetually baked by starlight and the other plunged into eternal darkness. These worlds become theaters of atmospheric drama. On the dayside of planets like Kelt 9b, temperatures soar above 4,000 degrees Celsius, hot enough to tear molecules apart. Meanwhile, the night side might host strange, slushy precipitation as gases that vaporized in the heat condense into exotic snow. Some models suggest these planets could develop colossal storm systems along their twilight zones, where opposing air masses collide in endless meteorological warfare. The weather patterns we're discovering rewrite the rules of planetary science. Take the case of WASP 76b, where daytime temperatures vaporize iron, allowing metallic clouds to form. As these iron-laden winds cross into the night side, the metal condenses and falls as rain, literal droplets of molten iron splashing across an alien landscape. Other worlds exhibit even stranger behavior. Diamond rain on Neptune-like exoplanets, where crushing pressures turn atmospheric carbon into glittering crystals that sink toward the core. What makes these discoveries so valuable isn't just their spectacle, it's how they reveal the incredible adaptability of physical laws. The same principles that create Earth's gentle breezes can, under different conditions, whip up eternal supersonic gales. By studying these extremes, we're building a universal understanding of how energy flows through planetary atmospheres, whether they're hydrogen-rich or filled with silicate vapors. Each bizarre weather pattern we uncover is another piece in the puzzle of how planets evolve, and what conditions might nurture or destroy the potential for life. Perhaps most fascinating are the worlds that challenge all our expectations. Some ultra-hot Jupiters appear to have temperature inversions layers where the atmosphere gets hotter with altitude instead of cooler. Others show evidence of global jet streams that funnel heat in ways we've never observed in our solar system. Then there's the mystery of puffy planets like HTP-1b, with atmospheres so extended and low density that they resemble cosmic cotton candy, where weather systems might operate in slow motion under weak gravity. These alien climates aren't just curiosities, they're teaching us about planetary resilience and change. A world with constant, violent storms might mix its atmosphere thoroughly, potentially distributing life-giving compounds across latitudes. Another with permanent high-pressure zones could develop stable regions where delicate chemical processes unfold uninterrupted. As we catalog more exoplanet weather systems, we're not just filling a cosmic atlas, we're learning the many languages in which planets write their stories across the stars. Tidal forces might seem like a distant concept, but their power to reshape worlds is anything but subtle. Take Jupiter's moon Europa, a frozen shell hiding a vast, liquid ocean beneath its icy crust. What keeps this water from freezing solid in the bitter cold of space? The answer lies in the relentless gravitational tug of war between Europa and its massive parent planet. As Europa orbits Jupiter, the gas giant's immense gravity stretches and squeezes the moon like cosmic putty, generating friction deep within its core. This constant kneading produces enough heat to maintain an ocean larger than all of Earth's combined, despite being over 480 million miles from the Sun. This phenomenon isn't unique to our solar system. Exoplanets orbiting close to their stars, especially those with elliptical paths, experience tidal heating on an even grander scale. Picture a world that swoops in close to its star before swinging far out again in a stretched orbit. Each close pass subjects the planet to intense gravitational stretching, while the distant phase allows it to relax. This rhythmic flexing pumps energy into the planet's interior like a cosmic exercise band, generating heat that could keep subsurface oceans churning for billions of years. Planets like these might look frozen and lifeless from the outside while harboring warm, watery depths where chemistry and perhaps even biology could thrive. The implications are staggering. Tidal heating expands the traditional habitable zone beyond the simple Goldilocks distance where liquid water can exist on a planet's surface. A frozen world orbiting a dim red dwarf star, far too cold for surface life under normal circumstances, could become a candidate for habitability if tidal forces keep its interior warm. Even rogue planets' worlds drifting through space without a host star might maintain liquid oceans through tidal heating if they're accompanied by large moons. The gravitational dance between such pairs could provide enough energy to stave off eternal frost. Some of the most promising candidates are super-Earths orbiting M-dwarf stars. These compact, fiery stars exert particularly strong tidal forces on nearby planets. Simulations suggest that tidal heating could power volcanic activity on such worlds, potentially creating hydrothermal vent systems similar to those on Earth's ocean floors and environments where life thrives without sunlight. The exoplanet LHS 1140b, for instance, might combine tidal heating with just enough starlight to create a thin layer of surface meltwater during its closest orbital approach, forming temporary oceans that freeze and thaw with its eccentric path. Yet tidal heating isn't always benevolent. Too much flexing can turn a world into a volcanic hellscape, with constant eruptions sterilizing its surface. Io, Jupiter's hyperactive moon, demonstrates this extreme. Its surface is a patchwork of molten lava lakes and sulfur plumes, heated so violently by tidal forces that it's the most volcanically active body in our solar system. The line between a life-giving heat source and a planetary pressure cooker depends on delicate balances of orbital distance, planetary composition, and gravitational interactions. What makes tidal heating so revolutionary is how it redefines our search for life. We're no longer limited to planets basking in their stars' glow. Now we must consider the hidden warmth of worlds squeezed by gravity's invisible hand. Future telescopes might detect indirect signs of this process, like unusual thermal emissions from apparently frozen exoplanets, or chemical imbalances in their atmospheres hinting at subsurface activity. Every moon, every eccentric orbit, every gravitational interaction becomes a potential clue in our quest to understand where life might be stirring in the cosmic dark. The search for life beyond Earth doesn't stop at exoplanets. There's a whole hidden frontier of worlds orbiting those worlds. Exomoons, the natural satellites of distant planets, could be cosmic oases in their own right, with conditions ripe for life even if their host planets are inhospitable. Think of Jupiter's moon Europa, with its subsurface ocean kept liquid by tidal forces, or Saturn's Titan, where methane rivers carve valleys beneath a thick nitrogen sky. Now imagine such moons circling planets light years away, each with its own recipe for habitability. The possibilities are as vast as they are tantalizing. Detecting these elusive objects is one of astronomy's greatest technical challenges. Unlike their host planets, exomoons are small, faint, and often lost in the glare of both the planet and its star. But scientists have developed ingenious ways to hunt for them. One method looks for subtle wobbles in a planet's transit signal, tiny timing variations that suggest the gravitational tug of an unseen moon. Another approach searches for secondary dips in starlight, faint echoes that might occur when a moon transits its star either just before or after the planet does. These techniques are pushing telescopes to their limits, but the payoff could be revolutionary. The most promising candidates are moons orbiting gas giants in the habitable zone. Picture a Jupiter-like planet with an Earth-sized moon. The moon could have a stable climate, protected by its host planet's magnetic field from stellar radiation, yet warmed enough by tidal heating to maintain liquid water. Kepler 1625b, for instance, is a potential exomoon candidate with hints of an extended atmosphere, possibly the first whiff of a lunar world with its own sky. Even more intriguing are rogue moons, orphaned from their parent planets and drifting through space, warmed solely by internal heat. These dark travelers could harbor subsurface oceans far from any star's warmth. What makes exomoons such compelling targets isn't just their potential for life, it's their diversity. A moon with a thick carbon dioxide atmosphere might trap enough heat to offset a dim star's feeble light. Another, bathed in ultraviolet radiation from a nearby gas giant, could develop protective organic hazes like Titans. Some might even have seasons driven by their planet's axial tilt, creating dynamic cycles of freezing and thawing. The sheer variety of environments possible on exomoons dwarfs what we've seen in our own solar system. The hunt for these hidden worlds is more than a scientific curiosity, it's a paradigm shift. If life can thrive on moons as easily as planets, the cosmic real estate for biology expands exponentially. Future telescopes equipped with next-generation spectrographs might one day analyze the atmospheres of exomoons, searching for oxygen, methane, or even industrial pollutants. The first definitive detection of an exomoon could rewrite the rules of where and how we look for life in the universe. After all, if a moon can outshine its planet in the search for habitability, we may need to rethink what Earth-like really means. Nature has a mischievous side when it comes to hiding the truth about alien life. Just because we spot oxygen or methane in an exoplanet's atmosphere doesn't automatically mean we've found biology at work. Volcanic eruptions can pump out oxygen-rich gases without a single organism involved. Starlight breaking apart water molecules high in an atmosphere might create free oxygen through pure chemistry. Even methane, a gas we associate with cows and microbes here on Earth, can seep out from geothermal vents or arrive via comet impacts, no life required. The universe is full of natural processes that mimic the very signals we associate with living worlds. Take Venus as a sobering example. Its atmosphere contains phosphine, a gas that, on Earth, is produced almost exclusively by anaerobic bacteria. When scientists first detected it in Venus's clouds, excitement surged, but further analysis revealed volcanic activity could potentially create the same signature under extreme conditions. Similarly, Titan's methane-rich atmosphere might resemble Earth's primordial chemistry, yet its frigid surface hosts no known life. These cosmic false alarms teach us a critical lesson. One intriguing gas isn't enough. True biosignatures require multiple lines of evidence, like oxygen coexisting with methane at ratios that defy geological explanations, or seasonal fluctuations that mirror biological cycles. The hunt for life demands more than just powerful telescopes. It requires scientific detective work of the highest order. When researchers spotted dimethyl sulfide in the atmosphere of K218b, a potential Hycean world, they didn't declare victory. Instead, they ran simulations to see if ocean chemistry or atmospheric processes could produce the same signal without life. Future missions will need to analyze not just what gases are present, but how they interact. Does the planet's carbon dioxide level drop during its equivalent of spring, suggesting photosynthetic activity? Are there complex organic molecules that decay too quickly to exist without constant replenishment? Even the presence of industrial pollutants like nitrogen dioxide could one day hint at technological civilizations, but only after ruling out every possible natural source. What makes this search so challenging and so thrilling is that every discovery forces us to expand our understanding of planetary chemistry. A gas that's a definitive biosignature in one context might be a red herring in another. That's why scientists now talk about agnostic biosignatures, patterns in atmospheric data that suggest something unusual is happening, even if we can't yet explain it. The next generation of telescopes won't just snap pictures of exoplanet atmospheres. They'll watch how those atmospheres evolve over years, tracking chemical reactions in real time. Only by observing the full symphony of planetary processes can we hope to distinguish between nature's clever forgeries and the real deal, a world where, against all odds, life has taken root. Behind every groundbreaking exoplanet discovery lies an invisible power, how supercomputer simulations that act as cosmic crystal balls. These digital laboratories let scientists play God with alien atmospheres, tweaking variables like gravity, starlight intensity, and gas mixtures to see how hypothetical worlds might behave. Imagine recreating the crushing pressures of a super-Earth or the supersonic winds of a hot Jupiter, not with telescopes, but with lines of code running on machines capable of quadrillions of calculations per second. When the James Webb Space Telescope beams back atmospheric data, it's these simulations that transform raw numbers into vivid planetary portraits. The magic happens through climate modeling adapted from Earth science but pushed to cosmic extremes. Researchers start with basic physics: how gases absorb heat, how winds redistribute energy, how clouds form under alien skies. Then they dial up the strangeness. What happens when a planet's year lasts only 10 Earth days, or when tidal forces keep one hemisphere locked in permanent daylight? Some models predict perpetual hurricane systems circling a planet's twilight zone, while others show how methane might cycle between a world's atmosphere and its hypothetical subsurface ocean. These virtual experiments help explain why certain exoplanets have bafflingly flat transmission spectra, suggesting ultra-high cloud decks, or why others show unexpected temperature inversions. One standout example is TRAPPIST-1e, an Earth-sized world in its star's habitable zone. Early observations hinted at possible water vapor, but was it enough for global oceans? Simulations tested hundreds of scenarios varying atmospheric thickness, carbon dioxide levels, even ocean coverage, to predict what Webb might detect. The results helped astronomers distinguish between a steamy greenhouse world and one with temperate seas. Similarly, models of lava planet K2-141b revealed its atmosphere could contain vaporized rock that condenses into glittering mineral clouds on the night side, a prediction later confirmed by spectral analysis. What makes these simulations indispensable is their ability to explore what-if scenarios beyond our current observational limits. Could a planet with 3 times Earth's gravity sustain breathable air? Might tidally locked worlds develop habitable pockets where winds balance extreme temperatures? Some models even suggest exotic climates like nitrogen-dominated atmospheres with liquid methane lakes, environments where life might follow entirely different chemical rules. By stress-testing these possibilities virtually, scientists know exactly where to point their telescopes when hunting for real examples. The future of exoplanet research hinges on this synergy between digital and observational astronomy. Next-generation models now incorporate atmospheric chemistry down to individual photon interactions, simulating how starlight at different angles might reveal seasonal changes in vegetation if alien forests exist. Others track how hypothetical microbial life could alter atmospheric gases over geologic timescales. As machine learning accelerates these simulations, we're not just predicting alien weather, we're preparing to recognize the faintest whispers of life in the cosmic dark. The next decade will transform exoplanet science from discovery into deep exploration, with telescopes so advanced they'll make today's instruments seem like primitive spyglasses. At the forefront stands the Extremely Large Telescope, or ELT, currently rising from Chile's Atacama Desert. With a mirror spanning 39 meters wider than a blue whale is long, this behemoth will capture starlight with such precision it could spot city lights on nearby exoplanets if they exist. Its spectrographs will dissect atmospheric molecules with unprecedented clarity, potentially detecting subtle biosignatures like chlorophyll or even artificial pollutants. But the ELT's greatest power lies in its ability to study Earth-sized planets around Sun-like stars. The holy grail of habitability searches that current telescopes struggle to observe. Meanwhile, the European Space Agency's Ariel mission will take atmospheric analysis to space in 2029, free from Earth's distorting air. Unlike general-purpose observatories, Ariel is a dedicated exoplanet atmosphere hunter, designed to survey 1,000 diverse worlds, from lava planets to icy giants, building the first comprehensive catalog of how planetary atmospheres evolve across cosmic environments. Its infrared eyes will peer through obscuring hazes that frustrate current telescopes, mapping temperature variations across tidally locked worlds and tracking how atmospheres respond to stellar flares. Ariel's secret weapon, the ability to monitor single planets for dozens of consecutive hours, watching their atmospheres churn and change in real time. These missions are just the opening act. NASA's Habitable Worlds Observatory, slated for the 2030s, will combine the light-gathering power of the ILT with the stable space environment of Ariel, using a coronagraph so advanced it can block parent stars' glare to directly image Earth twins. Early designs suggest it could resolve continents and clouds on planets within 30 light-years. Even more ambitious concepts lurk in planning stages. Starshades flying 40,000 kilometers from telescopes to create artificial eclipses, or interferometers linking multiple spacecraft to achieve impossible resolution. The true revolution lies in how these tools will work together. ILT's ground-based observations will identify prime targets for Ariel space-based scrutiny, while both feed data to the Habitable Worlds Observatory for deep dives. This multi-telescope network will cross-validate discoveries, eliminating false positives that plague single-instrument studies. Imagine confirming an oxygen-rich atmosphere with one telescope, then using another to check for industrial chemicals or artificial light patterns, building a case for life piece by irrefutable piece. Beyond hardware, new analysis techniques are rewriting what's possible. Machine learning now sifts through decades-old telescope data, uncovering missed planetary signals or predicting atmospheric compositions before observations begin. Quantum computing promises to simulate entire exoplanet climates atom by atom, revealing how alien weather systems might distribute life's building blocks. Citizen science projects like Planet Hunters continue to enlist the public, proving that some planetary discoveries still rely on human pattern recognition no algorithm can match. This golden age isn't about finding more planets, it's about understanding them intimately. Future telescopes won't just count worlds, they'll chronicle their life stories, from molten infancy to potential biological awakening. With each technological leap, we're not just building better instruments, we're extending our senses across the light years, turning distant specks into places with weather, chemistry, and maybe even neighbors. The universe's planetary tapestry is richer than we ever imagined, and soon we'll be able to read every thread. Some of the most groundbreaking exoplanet discoveries didn't come from professional astronomers. They came from everyday people sitting at their kitchen tables. Projects like Planet Hunters prove you don't need a billion-dollar telescope or a doctorate to contribute to cutting-edge science. This global citizen science initiative invites anyone with an internet connection to sift through data from NASA's Kepler mission, scanning light curves for the telltale dips that signal a planet's presence. It's like a cosmic version of Where's Waldo, except instead of a striped shirt, you're hunting for shadows cast by worlds light years away. The results speak for themselves. Amateur volunteers have spotted planetary candidates that algorithms missed, including the remarkable seven-planet system K2-138, a discovery that made headlines worldwide. What makes these citizen scientists so effective? Human eyes excel at pattern recognition, catching subtle anomalies that rigid computer programs might dismiss as noise. One schoolteacher in the UK noticed irregularities in a star's brightness that turned out to be an entirely new category of exoplanet, a warm Jupiter orbiting surprisingly close to its star. Another volunteer, a retired radio technician, identified multiple planetary candidates just by spending evenings analyzing data as a hobby, but the impact goes beyond individual discoveries. Crowdsourcing accelerates research exponentially. While professional astronomers might focus on high-priority targets, thousands of volunteers can scrutinize vast datasets in parallel, flagging unusual systems for further study. Projects like Exoplanet explorers on Zooniverse have processed millions of classifications in months' work that would take a single researcher lifetimes. This distributed approach also democratizes science, breaking down barriers between academia and the public. A high school student in Indonesia can now contribute meaningfully to astrophysics, no university affiliation required. The tools available to amateur astronomers keep evolving. Free software like AstroImage lets enthusiasts analyze telescope data with professional-grade precision. Online communities share techniques for refining observations, turning backyard telescopes into planet-hunting instruments. Some amateurs even collaborate on professional papers, their names listed alongside career scientists, proof that meaningful research isn't confined to institutions. The recent discovery of a gas giant by the Habitable Exoplanet Hunting Project, a network of amateur telescopes across 4 continents, shows how grassroots efforts can rival professional surveys. What makes citizen science truly special is how it transforms passive observers into active explorers. Every time someone clicks through Kepler data or adjusts their telescope's focus, they're participating in humanity's oldest quest to understand our place in the cosmos. These projects remind us that science isn't just about elite experts in ivory towers. It's a shared human adventure powered by collective curiosity. The next exoplanet discovery might come from a taxi driver in Nairobi, a baker in Montreal, or maybe even you, because in this new era of astronomy, the universe belongs to everyone. The cosmic silence is deafening. With billions of potentially habitable planets in our galaxy alone, the absence of alien radio signals or interstellar visitors raises one of science's most haunting questions: where is everybody? This is the Fermi paradox, the striking contradiction between the high probability of extraterrestrial civilizations and our complete lack of evidence for them. Named after physicist Enrico Fermi, who famously asked, "But where is everybody?" during a lunchtime conversation in 1950, this puzzle has spawned theories ranging from the sobering to the spine-chilling. One possibility is that life is far rarer than we think. Even with countless Earth-like exoplanets, the leap from simple chemistry to complex biology might require such a precise series of cosmic accidents that we're effectively alone. Imagine winning the lottery 100 times in a row. That's the level of statistical luck some scientists believe is needed for intelligence to emerge. Others argue that while microbial life could be common, technological civilizations might be extraordinarily fragile. Climate catastrophes, asteroid impacts, or self-inflicted disasters like nuclear war could snuff out advanced societies before they ever develop interstellar travel. Then there's the darker explanation. What if civilizations actively hide? A universe filled with predators, whether artificial intelligences or hostile aliens, might force survivors into radio silence. This zoo hypothesis suggests we're being deliberately ignored or quarantined, like animals in a galactic nature preserve. Alternatively, advanced beings might have evolved beyond physical forms we'd recognize, existing as digital consciousnesses or energy patterns that don't interact with the material universe as we know it. Exoplanet research offers a glimmer of hope for solving this riddle. If we discover even simple life on a nearby world like Mars or Europa, it would suggest biology sparks easily, making the silence of advanced civilizations even more puzzling. Finding complex atmospheric chemistry on distant exoplanets could hint at industrial activity, while detecting artificial megastructures around stars might reveal civilizations harnessing stellar energy. The absence of such signs in our growing exoplanet catalog would point toward the Great Filter, a hypothetical stage so difficult to surpass that almost all life fails to advance beyond it. For now, the Fermi paradox remains a mirror reflecting our own existential questions. Are we the universe's firstborn, destined to spread life through the void? Or are we the last survivors of a cosmic cycle of emergence and extinction? Every exoplanet we study carries not just scientific data, but philosophical weight. The answers, or continued silence, will shape how humanity sees its place in the cosmos for generations to come. Crossing the void between stars isn't just a challenge, it's a humbling reminder of how vast the cosmos truly is. With our current rockets, a trip to even the closest exoplanet, Proxima Centauri b, would take over 75,000 years. That's longer than all of recorded human history. Conventional chemical propulsion, the kind that took us to the moon, simply can't generate enough speed to make interstellar travel practical within a human lifetime. The distances are so immense that traveling at the speed of sound would still leave you drifting through emptiness for millions of years before reaching another star system. But where conventional technology fails, imagination thrives. Enter light sails silvery sheets thinner than a human hair, designed to catch the push of photons from powerful lasers. Unlike rocket fuel, light sails never run out of momentum as long as the beam stays focused. Breakthrough Starshot, backed by visionary Yuri Milner and the late Stephen Hawking, aims to capitalize on this with a daring plan: launch a fleet of gram-sized star chips propelled by a 100-gigawatt laser array. These tiny probes, each no larger than a postage stamp, could theoretically reach 20% the speed of light, arriving at Proxima Centauri in just 20 years. Imagine receiving close-up images of an alien world within our lifetime. Of course, the engineering hurdles are staggering. A laser that powerful would need to be more energetic than all sunlight hitting Earth's surface. The sail material must reflect 99.999% of incoming light to avoid vaporizing instantly. Even cosmic dust becomes a deadly hazard at relativistic speeds. A grain of sand could obliterate a probe traveling at 134 million miles per hour. Then there's the challenge of transmitting data back across 4 light-years with a device the size of a fingernail. Yet these aren't deal-breakers, they're puzzles waiting for solutions. Humanity's first interstellar missions might look nothing like the crude starships of science fiction. Instead of massive vessels with warp drives, we could send self-replicating nanobots that build infrastructure upon arrival using local materials. Or harness nuclear pulse propulsion riding controlled explosions like Project Orion envisioned in the 1960s. Some theorists even speculate about tapping into quantum entanglement for communication, bypassing light speed delays entirely. What makes these concepts more than just pipe dreams is their power to inspire real-world innovation. The same laser technology propelling light sails could deflect asteroids or beam clean energy across continents. Miniaturized probes are already revolutionizing planetary science. NASA's upcoming lunar flashlight mission uses a briefcase-sized satellite to map moon ice. Every seemingly outlandish idea pushes engineers to develop lighter materials, more efficient power systems, and smarter automation. For now, visiting an exoplanet remains firmly in the realm of imagination. But history shows that today's impossibilities often become tomorrow's headlines. The Wright brothers first flew fewer than 12 seconds a century later. We had jets crossing oceans in hours. If that same exponential progress applies to spaceflight, who's to say what breakthroughs await? The dream of touching another world isn't just about reaching distant stars, it's about proving that no horizon is forever out of reach. Detecting life on another world would be one of humanity's most profound moments, but what comes next could define our future for centuries. The question isn't just can we communicate with aliens, but should we? Picture this: after decades of searching, we finally receive a clear biosignature from a nearby exoplanet. The world erupts in celebration until someone asks, do we hit reply? Suddenly, scientists, governments, and philosophers are thrust into a debate with no easy answers. On one side, visionaries argue that reaching out is our destiny, a chance to share knowledge, forge alliances, or even secure our species' survival. On the other, skeptics warn of existential risks. What if our message attracts a civilization far more advanced and far less friendly than our own? History offers sobering parallels. When European explorers made first contact with indigenous societies, the results were often catastrophic, not out of malice, but from mismatched technology and disease immunity. Now imagine that scenario played out on an interstellar scale. Even a well-intentioned alien civilization might inadvertently harm us, whether through biological contamination, cultural disruption, or simply by existing as a technological superpower we can't comprehend. The late Stephen Hawking famously compared contacting aliens to Columbus landing in the Americas, suggesting it didn't turn out well for the Native Americans. Yet the silence carries its own risks. If every civilization chooses to hide, the universe becomes a cosmic library where no one dares speak. We might miss the chance to learn from species that solved problems we haven't even encountered yet: climate collapse, energy scarcity, or the philosophical challenges of artificial intelligence. Some researchers propose active SETI, search for extraterrestrial intelligence, deliberately beaming messages to promising star systems. These efforts, like the Arecibo message sent in 1974 or the recent transmissions toward Proxima Centauri, are essentially interstellar handshakes carefully crafted to convey basic math and science, avoiding anything that could reveal Earth's vulnerability. The protocols governing this dilemma are surprisingly sparse. The United Nations Outer Space Treaty vaguely mandates avoiding harmful contamination of celestial bodies, but says nothing about two-way communication. Informal guidelines, like those drafted by the International Academy of Astronautics, suggest international consultation before replying to signals, yet no enforcement mechanism exists. In a world where private companies and amateur astronomers could theoretically broadcast whatever they please, the lack of global coordination is startling. Imagine a teenager with a radio telescope accidentally triggering an interstellar incident because no one thought to regulate cosmic messaging apps. Perhaps the most compelling argument for caution isn't fear, it's responsibility. If life is rare, we might owe it to the universe to protect emerging civilizations, including our own, from premature contact. Alternatively, if intelligence is common but fleeting, snuffed out by war, environmental collapse, or some unknown great filter, then reaching out could be a desperate bid to find allies before it's too late. The irony is crushing. The very act of searching for aliens might reveal whether we're destined to join them or join the cosmic silence. For now, the debate remains theoretical, but not for long. As telescopes grow more powerful, the day we detect life, or it detects us, draws nearer. When that moment comes, humanity will face a choice unlike any other: to speak or to listen, to risk or to retreat. The answer won't just define our relationship with aliens, it will define who we are. Those long strings of letters and numbers attached to exoplanets Kepler 452b, HD 209458b, aren't just random gibberish. They're cosmic addresses, telling scientists exactly where to find each world in the vast stellar catalogue. The first part usually honors the telescope or survey that discovered it, like Kepler or TESS. The following numbers pinpoint the host star's identity in astronomical databases, while the lowercase letter reveals the planet's order of discovery around that star. B marks the first planet found, C the second, and so on down the alphabet. It's a system born out of necessity. With thousands of new worlds being logged every year, you need something precise and scalable, even if it doesn't exactly roll off the tongue. But amid this sea of technical designations, a few exoplanets have earned more poetic monikers. Take PSRB 1620-26b, a planet orbiting a pulsar that's older than our solar system. Astronomers nicknamed it Methuselah, after the biblical figure who lived for 969 years, a fitting tribute to a world that survived unimaginable cosmic upheaval. Then there's Osiris, the informal name for HD 209458b, the first exoplanet confirmed to have an evaporating hydrogen atmosphere. These names aren't official, but they stick because they capture the imagination in ways that alphanumeric codes never could. Occasionally, the public gets to weigh in directly. The International Astronomical Union has hosted naming contests where schools and astronomy clubs propose and vote on titles for particularly notable exoplanets. One winning entry, Galileo, for a Jupiter-like world, honoring the astronomer who first observed Jupiter's moons. Another contest dubbed a scorching hot gas giant, Nightingale, inspired by its star's name, Kepler 1604, which resembled the musical term solfege. These initiatives do more than just replace sterile catalog numbers. They weave human stories into the fabric of distant worlds. Imagine stumbling upon a true Earth twin, a blue and green marble with continents, oceans, and perhaps even city lights visible from space. What name would do it justice? Eden, pale blue dot 2. The choice would carry enormous weight, shaping how generations think about humanity's place in the cosmos. Future historians might look back on that moment as the instant our perspective truly shifted, when another Earth stopped being science fiction and became a place with its own identity, waiting to be explored. Until then, every Kepler and toy in the databases represents not just data points, but possibilities, worlds that might one day bear names as familiar as Mars or Venus, once we learn enough about them to know what they're really like. The Drake equation has been astronomy's most tantalizing thought experiment since Frank Drake first scribbled it on a chalkboard in 1961. At first glance, it looks deceptively simple, a string of variables multiplied together, each representing a cosmic hurdle life must overcome to become detectable. But behind those symbols lies the weight of humanity's deepest curiosity. Are we alone? The equation's beauty is in its flexibility. Every new exoplanet discovery doesn't just add to our catalog of worlds, it sharpens the numbers we plug into this cosmic calculator, turning speculation into something approaching science. Take the very first variable, the rate of star formation in our galaxy. Thanks to telescopes like Gaia, we now know the Milky Way churns out about 7 new stars per year. That's a solid starting point, but it's the next factors where things get spicy: the fraction of stars with planets. Just 30 years ago, this was a giant question mark. Today, after missions like Kepler and TESS, we're confident nearly every star hosts at least one world, with many boasting entire planetary systems. That single update alone multiplies the equation's potential output by orders of magnitude. Then comes the habitable zone factor, the orbital sweet spot where liquid water could exist. Here's where exoplanet diversity throws us curveballs. Red dwarfs, the galaxy's most common stars, have habitable zones so close that planets there risk being tidally locked or ravaged by flares. Hotter stars offer wider, more stable zones but burn out faster. Every new Goldilocks planet we find, from TRAPPIST-17 rocky worlds to the enigmatic K218b with its water vapor-rich atmosphere, refines our estimate of how many worlds could theoretically host life. But the equation's real drama lies in its later terms, the leap from habitable conditions to actual biology, then to intelligence, and finally to civilizations advanced enough to communicate. These remain stubbornly blank pages in our cosmic ledger. The discovery of even simple microbial life on Mars or Europa would suggest biology sparks easily, boosting the odds. Conversely, if we scan 1,000 Earth-like exoplanet atmospheres and find zero biosignatures, the grim implication is that life might be extraordinarily rare, or that intelligent life tends to self-destruct before going interstellar. What makes the Drake equation timeless isn't its ability to give definitive answers, it's how it evolves alongside our knowledge. When JWST detects a bizarre atmospheric chemical or we stumble upon a technosignature, we're not just collecting data, we're assigning probabilities to humanity's cosmic significance. The equation forces us to confront our assumptions. Is life a statistical inevitability given enough time and space, or are we the universe's one in a trillion accident? With each passing year, as our telescopes peer deeper and our models grow sharper, we're not just solving an equation, we're writing the story of life itself. Picture a world where the sky burns crimson at midday, with twin suns casting violet shadows across jagged crystalline plains. This isn't a scene from a sci-fi movie. It's a scientifically informed painting of exoplanet Kepler 16b, created by artists working hand in hand with astronomers. These collaborations transform columns of data and spectral graphs into breathtaking vistas, giving us glimpses of places we may never visit. When telescopes detect a planet's mass, orbit, and atmospheric composition, artists step in to ask, what would it feel like to stand there? How would the light filter through alien clouds? The answers lie at the intersection of hard science and boundless imagination. Take the iconic blue marble image of Earth, a single photograph that reshaped how humanity views its home. For exoplanets, direct images are vanishingly rare, so artists become our interstellar photographers. They start with known facts: a planet's size, its star's color and temperature, the gases present in its atmosphere. Then comes the creative alchemy. A world with high methane levels might sport hazy orange skies, while a carbon-rich planet could have diamond mountains glittering under a soot-colored sun. The lava world 55 Cancri E inspired one striking depiction where molten rock rivers reflect the glow of a colossal nearby star, creating an eternal twilight of fiery hues. These visualizations do more than dazzle. They serve a vital scientific purpose. By rendering theoretical climates in vivid detail, artists help researchers spot flaws in their models. An atmosphere that looks implausibly uniform in a painting might reveal gaps in our understanding of wind patterns or cloud formation. Public engagement soars when abstract concepts become tangible worlds. NASA Visions of the Future posters, featuring tourist-style ads for exoplanets like TRAPPIST-1e, have become cultural touchstones, blending humor, science, and art to spark curiosity. Yet every artistic choice carries weight. Should a tidally locked planet's dark side be depicted as frozen wasteland or lit by bioluminescent lifeforms, how might vegetation appear under a red dwarf's dim glow, black to absorb all available light or translucent to avoid overheating? Some artists hypothesize photosynthetic aliens using infrared radiation, painting forests in shades beyond human vision. Others imagine silicon-based lifeforms with crystalline structures that glitter like living geodes. The most compelling works balance educated speculation with humility, reminding viewers that reality will likely outshine our wildest dreams. The next time you see an exoplanet illustration, look closer. Those swirling clouds or jagged coastlines aren't random, they're hypotheses made visible. When the James Webb Telescope detected water vapor on K218b, artists worldwide raced to depict its hypothetical Haitian world, global oceans beneath a hydrogen-rich sky, perhaps with icebergs floating under the glare of a cool dwarf star. These images become time capsules, evolving as new data emerges. What began as a blurry pixel in a telescope's eyepiece transforms into a place with weather, geography, and maybe, just maybe, the stirrings of life. Buying a piece of an exoplanet might sound like science fiction, but right now, you can purchase a deed to your very own patch of alien real estate online, no spaceship required. These novelty certificates might not hold legal weight, but they reveal something fascinating about human nature. We're already dreaming of the day when distant worlds become destinations. While today's exoplanet deeds are little more than imaginative keepsakes, they force us to confront a question we can't ignore much longer: who gets to claim the cosmos? The Outer Space Treaty of 1967, signed at the height of the Cold War, declares that no nation can own celestial bodies. But this landmark agreement never anticipated private companies mining asteroids or tourists visiting Mars. Now, with exoplanet discoveries accelerating, legal experts are racing to define what ownership even means beyond our solar system. Could a future Elon Musk stake a claim on a habitable super-Earth? Might corporations patent alien microorganisms for profit? The law, as it stands, is woefully unprepared for the ethical and logistical dilemmas interstellar exploration will bring. Consider the precedent set by Earth's own history. The age of exploration saw European powers divide continents with little regard for indigenous populations, a cautionary tale about how not to approach new frontiers. Some ethicists argue that exoplanets should be protected as cosmic heritage sites, off limits to development entirely. Others propose a first caretaker model, where those who establish sustainable outposts gain stewardship rights without outright ownership. The wild card, artificial intelligence. If autonomous probes terraform or build infrastructure before humans arrive, who gets credit, the machines, their creators, or all of humanity? The business potential is staggering. Luxury orbital hotels are already in development for Earth's wealthy elite, but exoplanet tourism would be in a league of its own. Imagine booking a millennium-long cruise to TRAPPIST-1e, where your descendants might one day stroll along alien beaches under a salmon-colored sky. Or virtual reality tours that let you walk the lava fields of 55 Cancri E from the safety of your living room. Startups are already trademarking names like Exovacations and Interstellar Getaways, betting that curiosity about these worlds will one day be worth trillions. Yet the biggest hurdle isn't legal or technological, it's biological. Even the closest exoplanet, Proxima Centauri b, is 4.2 light-years away. At current speeds, that's a 75,000-year journey. Unless we crack faster than light travel or hibernation technology, interstellar tourism may remain the ultimate bucket list item no one can actually check off. But that hasn't stopped visionaries from planning. Architects sketch floating cities for gas giants, while biologists speculate about memory hotels where your consciousness could be uploaded to an android body for the trip. What makes this more than just futuristic fantasizing is how it reshapes our perspective today. Every time we look at an exoplanet's atmospheric data or debate its legal status, we're rehearsing for a future where humanity becomes an interstellar species. The cosmos might not have deed offices or border patrols yet, but the way we answer these questions now will determine whether we expand into space as thoughtful explorers or repeat the mistakes of our terrestrial past. One thing's certain, the universe isn't just a frontier, it's the ultimate mirror reflecting back who we are and who we aspire to become. Venus hangs in our solar system like a warning beacon, a world nearly identical in size to Earth, yet transformed by a runaway greenhouse effect into a 500-degree hellscape. Its thick carbon dioxide atmosphere traps heat with terrifying efficiency, offering a glimpse of what happens when climate feedback loops spiral out of control. But here's the twist. Venus isn't just a cautionary tale for Earth, it's become a Rosetta Stone for deciphering exoplanet atmospheres. By studying how Venus went wrong, scientists are uncovering universal principles about planetary climate stability that apply far beyond our solar system. The parallels are chilling. When astronomers analyze distant worlds like the scorching hot Jupiter Kelt 9b, where daytime temperatures exceed 4,000 degrees Celsius, they see the same physics at work, greenhouse gases turning atmospheres into thermal prisons. Even more telling are the Venus Zone exoplanets orbiting perilously close to their stars, where water vapor and carbon dioxide could trigger irreversible heating. These alien laboratories demonstrate how narrow the habitable window really is. A planet just slightly closer to its star, or with slightly more atmospheric carbon, can tip from temperate to torrid in geological eye blinks. Yet exoplanets also reveal unexpected climate resilience. Take the super-Earth JJ1214b, shrouded in steam yet potentially harboring a deep-water ocean beneath its haze. Or tidally locked worlds like TRAPPIST-1e, where atmospheric circulation might redistribute heat to create habitable twilight belts. These discoveries prove that climate systems have surprising buffers mechanisms that could either save a planet from Venus's fate or lull its inhabitants into complacency before disaster strikes. The greatest lesson from exoplanet climatology isn't doom, it's perspective. Every atmospheric analysis underscores how delicate Earth's equilibrium truly is. Our planet's climate didn't stabilize by accident. It's the product of finely tuned balances between volcanism, weathering, and biological activity over billions of years. Exoplanet research has exposed a universal truth. Habitable worlds aren't default settings, they're cosmic miracles. When telescopes spot distant planets with oxygen-rich atmospheres, we're not just looking at potential alien homes, we're seeing reflections of our own world's precarious perfection. This cosmic context makes Earth's current climate crisis feel both more urgent and more solvable. If a single civilization on one fragile planet can decode atmospheric physics across the galaxy, surely we can apply that knowledge to preserve our own thin blue line. The same spectrometers analyzing methane on HD 189733b are monitoring greenhouse gases in our skies. The difference, we're the first species in known existence with both the power to understand climate threats and the agency to stop them. Exoplanet science isn't just about finding other Earths, it's about keeping ours. Scientists hunting for an Earth twin aren't just looking for any planet, they're searching for one that ticks every box. Rocky, Earth-sized, orbiting safely in the habitable zone, with an atmosphere capable of nurturing life as we know it. The discovery of Proxima Centauri b sent shockwaves through the astronomy community, a world roughly Earth's mass, just 4.2 light-years away, basking in the dim glow of our nearest stellar neighbor. But there's a catch. This planet orbits so close to its red dwarf star that it's likely tidally locked, with one side perpetually scorched and the other frozen in darkness. Still, models suggest its twilight band could harbor temperate pockets where liquid water might pool under alien skies. Then there's the TRAPPIST-1 system, a cosmic jackpot with 7 Earth-sized worlds crammed into orbits smaller than Mercury's. 3 of these TRAPPIST-1e, F, and G sit snugly in the star's habitable zone. Early spectroscopic hints suggest E might have a water-rich atmosphere, while F could host global oceans beneath icy shells. But again, complications arise. Red dwarfs like TRAPPIST-1 unleash violent flares that could strip atmospheres over time. Without robust magnetic fields or thick atmospheric blankets, even a perfectly positioned planet might end up as a barren wasteland. The Holy Grail remains a true Earth analog, a planet orbiting a sun-like star at just the right distance, with stable seasons, protective magnetosphere, and an oxygen-rich atmosphere. Kepler 452b came close, earning the nickname Earth's cousin for its size and orbit around a G-type star similar to our Sun. But it's over 1,400 light-years away, making atmospheric studies nearly impossible with current tech. KOI 456.02 offers another tantalizing candidate, nearly identical in size and temperature to Earth, though its star's intense activity raises doubts about long-term habitability. What makes this search so electrifying is how rapidly the field is advancing. 10 years ago, detecting any Earth-sized planet felt like science fiction. Now, next-gen telescopes like the Habitable Worlds Observatory aim to directly image dozens of potential twins, analyzing their atmospheres for signs of oceans, continents, and even vegetation. The statistical probability is staggering, with billions of Earth-sized planets estimated in our galaxy alone. The question isn't if we'll find a true twin, but when. Yet the deeper we look, the more we realize Earth's perfection is a delicate balancing act. Plate tectonics recycle carbon to regulate temperatures. Our large moon stabilizes the axial tilt, preventing wild climate swings. Jupiter's gravity deflects asteroids that might otherwise pummel us. An Earth 2.0 wouldn't just need water and air, it would need a similar symphony of cosmic luck. Every new candidate, whether promising or flawed, teaches us just how rare or how common our pale blue dot might truly be. Some exoplanets don't just bend the rules, they snap them in half. Take the case of HAT-P1b, a world so bafflingly inflated that scientists initially doubted their own measurements. This gas giant orbits its star every 4.5 days, yet its atmosphere balloons to nearly twice Jupiter's size despite having less mass. It's as if someone took a planetary core and wrapped it in cosmic cotton candy. The leading theory, intense stellar radiation pumps heat deep into the planet's interior, causing its outer layers to puff up like a soufflé in an oven. But here's the twist. Other hot Jupiters under similar stellar bombardment don't exhibit this extreme inflation, leaving astronomers scratching their heads over what special ingredient makes these worlds so inexplicably fluffy. Then there's the curious case of Kelt 16b, a planet that shouldn't exist at all. This ultra-hot Jupiter orbits so close to its star that its atmosphere is literally evaporating, leaving behind a comet-like tail of vaporized metal. Yet somehow, against all odds, it survived for billions of years. Conventional models predict such planets should have spiraled into their stars long ago, consumed by tidal forces. Their persistence hints at gaps in our understanding of orbital dynamics. Perhaps unseen companion planets or magnetic interactions act as cosmic stabilizers. Every time we think we've cracked the code of planetary survival, these stubborn worlds rewrite the playbook. Orbital anomalies add another layer of intrigue. The planet HD 80606b follows not a neat ellipse, but a wild, comet-like path that brings it scorchingly close to its star before flinging it back out into the frigid depths of its system. This extreme eccentricity defies standard planet formation theories. No calm, swirling protoplanetary disk could birth such a chaotic orbit. One provocative explanation suggests it was hurled into this roller coaster trajectory by a near collision with another giant planet, a gravitational slingshot frozen in time. These cosmic billiard shots force us to reconsider how violent and unpredictable young planetary systems can be. Even more perplexing are the Tatooine planets orbiting binary stars. While Kepler 16b's dual suns create picturesque sunsets, other circumbinary systems behave bizarrely. Some planets wobble like spinning tops due to their stars' competing gravitational tugs, while others follow figure-8 paths that make Newton's equations shudder. The real head-scratchers are planets like Kepler 491b, which orbits one star of a binary pair while the second star pirouettes wildly at a distance, a configuration so unstable that supercomputer simulations struggle to explain how it hasn't torn itself apart. What makes these mysteries so thrilling isn't just their strangeness, it's how they reveal the limits of our knowledge. Each anomaly is a cosmic breadcrumb leading to deeper truths about planetary formation, atmospheric physics, and celestial mechanics. When we encounter a planet that defies categorization, like the recently discovered TOI 821b, a world with the density of styrofoam, we're forced to invent new theories or radically revise old ones. These aren't just puzzles to solve, they're invitations to explore uncharted territories of astrophysics, where the next discovery might overturn everything we thought we knew about how planets live, die, and dance through the cosmos. Life on Earth has a knack for showing up in places we never thought possible: boiling hydrothermal vents at the bottom of the ocean, acidic pools that can dissolve metal, even the frozen wastelands of Antarctica where temperatures plunge to -80 degrees Celsius. These extreme survivors, called extremophiles, have rewritten biology's rulebook, proving life isn't just resilient, it's downright stubborn. When we search for life beyond our planet, these earthly outliers become our most valuable guides. If organisms can thrive in sulfuric acid or radiation-blasted rocks here, why not in the methane lakes of Titan or the subsurface oceans of distant ice worlds? Consider the humble tardigrade, a microscopic creature that can survive the vacuum of space, extreme dehydration, and even lethal doses of radiation by entering a state of suspended animation. Or the archaea living in Yellowstone's scalding hot springs, thriving in water nearly acidic enough to burn through steel. These organisms don't just endure harsh conditions, they've evolved to exploit them, turning toxic chemicals into energy sources and using extreme heat to drive their biological processes. Their existence forces us to reconsider what habitable really means. A planet doesn't need to be a cozy Earth twin to host life. It just needs the right combination of energy, liquid, and chemical building blocks, no matter how alien the environment seems. This perspective opens breathtaking possibilities for exoplanet science. A world like Venus, with its crushing atmospheric pressure and acid clouds, might harbor microbial life floating in its temperate upper layers. Frozen moons like Europa or Enceladus, with their subsurface oceans heated by tidal forces, could host entire ecosystems powered by hydrothermal vents, just like those in Earth's deepest trenches. Even rogue planets drifting through interstellar space without a host star might retain enough geothermal heat to sustain subsurface life for billions of years. The key lies in recognizing that life adapts to its environment, not the other way around. On a planet with perpetual darkness, organisms might evolve to sense infrared radiation instead of visible light. In a high-pressure hydrogen atmosphere, cell membranes could form from exotic lipids we've never encountered. Some scientists even speculate about shadow biospheres, life forms using entirely different biochemistry, like silicon-based compounds instead of carbon, lurking undetected in plain sight. Every new extremophile discovered on Earth expands the cosmic real estate where we might find life. The bacteria Desulforudes audaxviator survives 2 miles underground, cut off from sunlight and surface nutrients by feeding on radioactive decay products. If life can hack energy from rocks in Earth's crust, why not on Mars or a distant super-Earth? This radical redefinition of habitability means we shouldn't just focus on planets with balmy temperatures and blue skies. We should be scanning volcanic worlds with silicate clouds, or frozen orbs with subsurface oceans, or even gas giants where microbes might float in the upper atmosphere. The implications are profound. If life emerges wherever conditions allow, no matter how extreme, then the universe could be teeming with organisms in environments we'd consider uninhabitable. Our search strategies must evolve accordingly. Instead of only hunting for Earth-like biosignatures like oxygen and methane, we might need to look for chemical imbalances that suggest unconventional metabolisms, excess sulfur compounds, strange isotope ratios, or unexpected atmospheric layers that hint at biological activity below. Perhaps the most humbling lesson from extremophiles is this: life doesn't care about our definitions. It will take root in the unlikeliest places, using whatever chemistry works, defying every assumption we make. As we explore exoplanet atmospheres for signs of biology, we're not just searching for life as we know it, we're learning to recognize life as we don't know it. And that realization might be the key to answering humanity's oldest question: are we alone? Public excitement about exoplanet discoveries often skyrockets when headlines announce Earth-like or habitable worlds, but the reality is far more nuanced than media reports suggest. Remember the frenzy around Proxima Centauri b? News outlets painted it as a tropical paradise just next door, when in truth, this planet likely faces extreme tidal locking and violent stellar flares that could strip away any chance of a stable atmosphere. The gap between scientific reality and public perception comes down to translation, what astronomers cautiously describe as potentially within the habitable zone, often gets simplified into second Earth by the time it reaches mainstream audiences. This communication challenge stems from how we define habitable. To scientists, it simply means a planet orbits at a distance where liquid water could theoretically exist, not that it actually has oceans, breathable air, or even a solid surface. Take Kepler 452b, frequently called Earth's cousin. While it orbits a sun-like star in the Goldilocks Zone, subsequent studies revealed it's probably a mini Neptune with a thick hydrogen envelope, making surface life impossible. The media rarely explains these critical distinctions, leaving the public with whiplash as initial optimism gives way to more sober reassessments. Even the term Earth-sized can be misleading. When a telescope detects a planet with roughly our planet's mass, headlines trumpet the discovery of an Earth twin, but mass alone says nothing about composition. A world could be Earth's exact weight yet consist entirely of water, iron, or molten rock. Gliese 491b, for example, matches Earth's mass but orbits so close to its dim red star that any atmosphere would have boiled away eons ago. Without context about atmospheric pressure, stellar activity, and geological cycles, these simplified labels create false expectations. The hype cycle isn't just harmless exaggeration, it has real consequences. Overblown claims erode public trust when subsequent studies inevitably dial back initial excitement. Remember the infamous alien megastructure star KIC 8462852. When unusual light patterns sparked speculation about extraterrestrial engineering, the story went viral only for follow-up research to suggest mundane dust clouds as the likely culprit. This pattern risks turning exoplanet science into a boy who cried wolf scenario, where legitimate future discoveries of biosignatures might be met with skepticism. Scientists themselves bear some responsibility for this disconnect. Press releases often emphasize the most sensational angles to secure funding and public interest, while burying caveats in technical language. When the TRAPPIST-1 system was discovered, institutions led with artist concepts of 7 balmy, ocean-covered worlds, not the complex realities of tidal heating and atmospheric erosion that might make most of them uninhabitable. This tension between accuracy and engagement leaves researchers walking a tightrope, oversimplify and mislead, or present nuanced truths that fail to capture imaginations. The solution isn't to dampen enthusiasm, but to redirect it. Instead of fixating on Earth comparisons, we should celebrate exoplanets for their astonishing diversity. A planet like WASP 76b, where it rains molten iron, is no less fascinating because it can't host life. It's a window into the incredible range of planetary possibilities. By shifting the narrative from "Is this another Earth?" to "What can this world teach us about cosmic evolution?" we foster both accurate science and enduring wonder. Critical thinking tools can help audiences navigate exoplanet news. When encountering claims about habitable planets, ask, has its atmosphere been confirmed? What type of star does it orbit? Are there estimates of surface pressure or radiation levels? Even better, seek out scientists communicating directly through blogs or podcasts, where they can unpack discoveries without soundbite constraints. The most profound revelations in exoplanet science aren't about finding Earth's twin, they're about discovering how many ways a planet can be, and in that diversity, glimpsing the true creativity of the universe. Imagine waking up to breaking news that scientists have confirmed the existence of alien life, not just microbes, but complex organisms thriving beneath the ice of a distant moon or floating in the acidic clouds of a Venus-like world. The implications would ripple far beyond laboratories and academic journals, striking at the very core of what it means to be human. For millennia, our civilizations have operated under the assumption that Earth is life's sole sanctuary, a belief woven into religions, mythologies, and scientific paradigms alike. The discovery of even simple extraterrestrial organisms would force us to confront an existential paradigm shift comparable to Copernicus displacing Earth from the center of the universe. Religious traditions would face profound questions. Would the discovery of alien microbes validate or challenge creation narratives? Some faiths might embrace the idea of a creator who seeded life throughout the cosmos, while others could struggle to reconcile extraterrestrial life with scripture that seems Earth-centric. Historical precedents offer clues. When Galileo's telescope revealed moons orbiting Jupiter, it sparked theological debates that lasted centuries. A modern confirmation of alien life might ignite similar reckonings, with some interpreting it as divine abundance and others as heresy. Philosophically, the discovery would force us to redefine life's uniqueness, human exceptionalism. The idea that we alone possess consciousness or souls would face unprecedented scrutiny. If life arises readily across the cosmos, what does that say about our place in it? Ethical frameworks would expand to include non-earthly beings, prompting debates. Do we have moral obligations to protect alien ecosystems? Should we intervene if we find primitive life struggling on a dying world? These questions mirror colonial-era dilemmas, but on an interstellar scale, with higher stakes and no historical guideposts. Culturally, reactions would vary wildly. Some societies might celebrate the news as proof of the universe's vitality, inspiring art, music, and literature that reimagines our cosmic connections. Others could retreat into isolationism, fearing contamination, biological or ideological, from beyond Earth. The internet would erupt with conspiracy theories, while governments scramble to establish protocols for potential contact. The very concept of humanity might expand to encompass a broader galactic identity, or fracture along new lines of belief and skepticism. Yet the most profound impact could be psychological. Learning we're not alone would either humble or terrify us depending on who or what we find. Microbial life would suggest we're part of a vast, interconnected biosphere. Intelligent life would raise darker possibilities. Are we the galactic newcomers, or are others out there watching us? The search itself has already reshaped us, fostering international collaborations like the Breakthrough Listen project and inspiring generations to look skyward with renewed wonder. Whether the answer unites or divides us may depend less on the aliens and more on how we choose to see ourselves in their light. The study of exoplanet atmospheres isn't just about collecting data, it's about rewriting the story of existence itself. Every time we analyze the light filtering through an alien sky, we're not just identifying gases, we're peering into the universe's grand experiment with life. Consider the recent detection of water vapor on K218b, a world 8 times Earth's mass. That discovery didn't just add another planet to the catalog, it forced us to ask, could life thrive under a hydrogen-rich sky in oceans deeper than our Mariana Trench? These aren't academic exercises, they're challenges to our very definition of what makes a world habitable. What makes this quest so revolutionary is how it collapses the distance between stars. A telescope's spectrograph doesn't just measure wavelengths, it becomes a time machine, showing us snapshots of potential futures. When we study Venus like exoplanets, we're glimpsing Earth's possible fate if climate change runs unchecked. When we find planets with oxygen but no obvious biology, we're forced to confront how little we truly understand atmospheric chemistry. Each observation is a mirror, reflecting back both the universe's possibilities and our own planet's fragility. The tools we've built for this search are marvels of human ingenuity. The James Webb Space Telescope can detect the heat signature of a molecule 1 trillion miles away. Machine learning algorithms sift through decades of stellar data to find planetary needles in cosmic haystacks. Yet for all our technology, the most humbling realization is how much we still don't know. Take the case of super puffs, planets with the density of cotton candy. These cosmic anomalies defy every model of planetary formation, proving that the universe still holds surprises no supercomputer can predict. But the true significance of this work transcends science. For generations, humanity has wondered whether we're alone in the cosmos. Now, for the first time in history, we're developing the tools to answer that question definitively. The implications are staggering. Finding even microbial life elsewhere would suggest the universe is teeming with biology. Discovering complex organisms would hint that intelligence might be a common cosmic trait. And if we uncover nothing, that silence would be equally profound, a reminder of how precious and rare our own existence might be. This isn't just astronomy, it's a philosophical revolution disguised as data points. Every atmospheric analysis carries the weight of centuries of speculation, from ancient stargazers to modern scientists. The breakthroughs ahead won't just come from bigger telescopes, but from our willingness to question assumptions. Maybe life doesn't need oxygen, maybe habitable zones are far wider than we thought, or maybe we'll find something so unexpected it shatters all our models. That's why we keep looking, not just for answers but for better questions, because the day we stop being surprised by the cosmos is the day we stop truly seeing it. The next chapter of this story is being written right now, in the light of distant stars and the ingenuity of those who dare to decode it. And if history is any guide, the universe still has wonders waiting that we've scarcely begun to imagine.